Look at that cute baby. How old?
One month old.
1 month old. Oh man, you're in it. You're like in the thick of it. How awesome. So we got through our first week and we're going to get through our second week really quickly here because we only have one lecture this week. Make sure you're staying on top of getting into mastering chemistry, doing the labs. I've had quite a few people say that they weren't sure where to do the labs. If you go ahead and review the first lecture, we talk about how to do that, but you do have to have a physical lab manual. So if you haven't gotten that yet, you want to get it. If you haven't turned something in, turn it in. Even if it's late, I will give a little bit of leeway on the first assignments, the first one assignment, because I know it can be a little bit tricky. Figure everything out. I'm sure you've got other classes besides just this one. Okay. Let me share my screen with you. Carrie, you got a question?
Yeah, the SIG digit worksheet and the scientific notation worksheet, are those just practice or do we need to turn those in?
At the very end of the lab? Are you talking?
I don't know. In the folder.
Those are just
folder where the lab is.
That's just additional help for you. Yeah. So when you on Moodle, there's like yeah, there's like a folder. That's all additional practice for you. And it's sometimes we may reference it.
Okay, great. Thank you.
But yeah. All right. Okay, so we left off talking about prefixes. We talked about King Henry died before drinking chocolate milk, right? So kilo, hecto, deca, base, deci, centi, milli. Just a way to kind of memorize those. We, in this class, usually stay within this, but know that there are some units that are prefixes rather that are bigger than this and some prefixes that are smaller than this. So you may see them occasionally on the homework and things like that, but I don't usually put on my tests things like tera and giga and femto. Usually keep them between the kilo and the milli. So when choosing a prefix, you want to choose a prefix, like if you have the option to, you want to choose a prefix that is appropriate for whatever your measurement is. So if you're measuring the length of a piece of hair, you probably don't want to use a kilometer for your prefix. Same thing they've got here. If you've got a chemical bond, specifically a short chemical bond, that's 1.2 times 10 to the negative 10th meters. There's two prefixes we could use. We could use either a pico, which is 10 to the negative 12th, or a nano, which is 10 to the negative 9th. Usually you want to go with the smaller one. And this is a smaller number because this is a negative exponent, 10 to the negative 12th. If we were to write this using the pico, it would say we have 120 picometers. So then we're not having to deal with the mess of decimals and things like that. And you may not know what a picometer is, but it's a little bit easier to relate measurements when you don't have these like really long trailing decimals. So, excuse me. One of the units that we look at is volume. In volume, we can represent it as like a liter. We can put prefixes on there, so liter, milliliter, kiloliter. But we can also talk about volume as a derived unit. And when I say derived unit, it means that it's coming from other units. So what is volume? Volume is length times width times height, right? If we had a box, we would measure those three things and multiply them by each other. So sometimes volume is measured using things like cubic meters, cubic centimeters, cubic millimeters. This one you see a lot in the medical field, cubic centimeters, centimeter cubed. That's the same thing as a cc. You know, administer 50 cc's, that's what that is there. If you do any yard work, you get your mulch delivered, not in yards, you get it delivered in cubic yards, right? Or you buy for it in a cubic yard, a yard by a yard by a yard. So don't get freaked out if you start seeing units with these third powers here. What that is indicating is that we're talking about a volume. Okay. So the next thing we're going to get into, which you really want to understand how to do this, because I feel like most of this class, not all of it, but a lot of this class is just this thing called dimensional analysis or unit conversions. So going from one unit to another, even when we're doing more complicated things like stoichiometry later on in the semester, we're still going to set it up in this very, very similar format and way. And so you may find that you can solve some of these easier problems just in your head, but I want you to get into the practice of setting it up using dimensional analysis. So problem solving and unit conversions. All right, so this page talks a little bit about critical thinking. Critical thinking is not something that I can give to you. It's not like an equation that you can memorize, but it is something that we can practice, and I can give you practice problems so that we can kind of massage the muscle of our critical thinking skills in our brain. Unit conversions, this word here, unit conversion, it means going from one unit to another. So a lot of times you'll be given something in, let's say, meters, and you don't want it in meters, you want it in kilometers, or you want it in inches. We're going to go through this process of converting from one unit to another. That's where we use dimensional analysis in this unit conversion. There's another way that we can solve problems, and that's if we have a specific equation. That would be something like the equation Q equals MCAT, which we'll talk about in a couple chapters. There's 4 variables. You get 3 of them and you solve for the 4th, right? Or density equals mass over volume. You have that equation, you plug the correct things in, and then you solve for the missing variable. So how you're going to attack a problem, really, you're going to look at it as either a dimensional analysis or a unit conversion type problem, or you're just plugging and chugging into an equation. So if we're going to convert, dimensional analysis is just a fancy way of setting something up so that the appropriate units cancel. So the things we don't want go away, and the things we do want all of a sudden appear. You always want to give your numbers a unit. So it's never a good idea to just write like 62. Are you talking about meters, volume? What does that have to do? So make sure you're adding units. And whenever you're doing calculations, even though because we're online, I'm not really going to see your calculations. I want you to be putting units on them because as we move down and things get a little more complicated, we can kind of get confused on what we're doing. So this is the skeletal structure for dimensional analysis. This is like this setup will probably get you through like 70% of the class if you can understand this. So when you're given a problem and you know, okay, I'm converting, you always want to state what your given information is and what you're trying to find. You take your given information, you're going to multiply it by this thing called a conversion factor. And a conversion factor is just an equality that we've already talked about. So it's 2 things that equal each other. So an example of a conversion factor, 1 inch equals 2.54 centimeters. Those 2 things are talking about the same length. Another example of a conversion factor, 1,000 liters equals 1 kiloliter, okay? How many conversion factors are there in the world? So many, all right? Usually I would have you guys memorize some of them, but because of the state of the class, you will be able to look up your conversion factors. But just make sure that you are getting your conversion factors from a good source. So your textbook, your lab manual, sometimes there are conversion factors online that are not correct. So just make sure you're getting from the right place. So we take our given information, we multiply it by some sort of conversion factor, and then we will end up with our information sought. This is a little bit easier to see. We have our given unit. We multiply it by our conversion factor in such a way that the given unit is on the bottom, because if we see this here is sort of sitting over an inferred 1, right? When you write the number 3, it's really, there's a 3 over a 1. It's an inferred. We don't write it though. So the given unit is above the fraction bar, and the given unit in the conversion factor is written in such a way that it's below the fraction bar. Those will cancel, and what is left with is the desired unit. So you end up getting your desired unit. Let's try a really simple problem that you're going to say, oh, I don't want to do all this work for it, but just to get this idea going. So how many inches are in 2 feet? I know. It's like, well, you just multiplied, right? Well, let's actually put it into our dimensional analysis. So whenever you're given a word problem, you're going to see me do this over and over, and I want you to do it. Write what your given information is and write what you're trying to find. So my given piece of information, and I'm not going to say just 2, I'm going to say 2.0 because I want to have at least 2 sig figs. So my given piece of information is that I have 2.0 feet. What I'm trying to find is inches. All right, is there some sort of equation to do this? No. What we need is a equality or a conversion factor. So I need to relate inches to feet here. Well, last I checked, 1 foot is equivalent to 12 inches, right? You may see this written as 1 foot is equal to 12 inches. That is saying the same thing. Now, this isn't very useful for dimensional analysis. I actually want to put this into a fraction. So there's 2 different fractions I can write. I can say 1 foot over 12 inches, or I can say 12 inches over 1 foot. And remember that this is, right, these 2 things equal each other. So anything divided by itself is equal to a value of 1. So we're not actually changing the magnitude of the value, we're just converting its units. So off of that equation we said given units times the conversion factor written in such a way that the given is on the bottom, the desired is on the top, and then the given and the given go away, and we should be left with desired. So what are my given units and my given piece of information? It's this 2 feet here, 2.0 feet. I'm going to multiply this by my conversion factor. Remember, there's sort of an inferred 1 underneath here. How do I want to use my relationship? Well, if feet are on the top here, I want to put feet on the bottom, right? Because then the units will cancel. So feet on the bottom, and I want to move towards inches. So between these 2, this is the one that works. So I'm going to add the numbers, 1 foot on the bottom, 12 inches on the top. Feet will cancel, and we will be left with a value of 24 inches. Now I know you may be thinking I could do that in my head in about 1 second, but the numbers will get more complicated than this. So I don't think about, oh, if I'm going from feet to inches, I multiply, and if I'm going from inches to feet, I divide. I just set it up in my dimensional analysis and let it tell me what to do. So anything that's above the fraction bars, you multiply. Anything below the fraction bars, you divide. So let's tweak this just a little bit. I want you to try this one. How many feet are in 6.1 times 10 to the 4 inches? I'll give you all about 2 minutes to work on that, or at least set it up. You know, and if you can't even do that, then write what's given, write what you're trying to find, maybe write the conversion relationship. Okay, so in this one, slightly different. You're given inches and you're trying to get into feet. So we're given that we have 6.1 times 10 to the 4th inches. Don't get freaked out by this. This is just scientific notation. We're trying to find feet. The relationship is still the same, right? 1 foot is equivalent to 12 inches. We start with our given information. So we have 6.1 times 10 to the 4th inches. I'm going to multiply it by this relationship, but I want inches this time to go on the bottom and I want feet to go on the top. Make sure you put the right number with the right unit. So it's 1 foot equals 12 inches, not 1 inch equals 12 feet. That's super common. Just make sure you're pairing them with the right unit. What happens to inches? Inches will go away and we'll be left with just units of feet. Now we need to plug this into our calculator. So what sometimes happens is students will go, okay, well, I'm going to move this out 1, 2, 3, 4 and fill it in and then write this number into my calculator. Don't do that. That's a waste of time. Instead, write it in your calculator just like this. So if you have a fancy graphing calculator, I don't, I have my cell phone. I'll show you how to do it on your cell phone too. But if you have a fancy graphing calculator, you can literally write it as 6.1 times 10 to the caret little 4. The way I like to put it in though is actually to use the EE button. So I will write it as 6.1 and then there's a button that has an EE. That EE is taking the place of the times 10 to the and the little caret. Okay, so that encompasses that whole thing. And then you just write 4. All right, you should have that on your iPhone as well. So if you got to turn your iPhone calculator to the side to expand it out, you'll see the EE button. It's underneath the log above the rand. So you'll take 6.1, you'll hit the EE and you'll write 4. You should end up with 61,000, okay? If you have any questions on how to get that into your calculator, let me know. If for some reason this was a negative value, like -4, let's say it was a tiny number, you would need to add the negative in the second character here, so -4. In this case, we're going to take our 6.1 EE4, 61,000. times 1 divided by 12. So we're going to divide it by 12. Anything below the fraction bars gets its division. And I end up with a number like this, 5083.3, and the 3 sort of goes on for infinity. So you have to round that to the correct number of significant figures. Remember that conversion factors, these are definitions. So this is infinite number of sig figs. So we're limited by what's going on here. This thing has 1, 2 sig figs, 2 sig figs. So I have to round this number to 2 significant figures. So I keep the 5, I keep the 0. The 8 tells the 0 to round up. So this becomes 5, 1, and then I have to put zeros in the place there. So 5,100 feet. I could also take this another step further and write it in scientific notation, 5.1 times 10 to the 3rd feet. I would really, really take either one there. That this is not such a big number that scientific notation isn't necessary. But if the problem explicitly said to write it in scientific notation, do that. As far as rounding is concerned, though, taking it from this long decimal number into a more refined sig fig, you have to do that. Okay, get in the habit of rounding to correct sig figs. Now, what are we doing in dimensional analysis? We're just multiplying and dividing by conversion factors. So you're really always going to go with whatever the given unit is. So before we move into more examples and stuff, any questions on the setup of that? I wanted to go with something that was relatively easy, or units that you're really comfortable with. So it's just a matter of canceling things out. Okay, if you do have questions at some point, you can throw them in the chat or turn your mute off. So the slides talk about, the relationship here between centimeters and inches. So 2.54 centimeters is equivalent to 1 inch. You can write it in a couple different ways. If we had something like 4.47 centimeters and we want to convert it into inches, we would use the relationship between centimeters and inches. So there are lots of conversion factors you can use. Remember, you're not changing the length in any way, you're just shifting the unit. So the slides and the text talk a lot about these things called solution maps, which is just a visualization of how you're going to get from your given to your final. When it's a one-stepper, you don't always need to do that, like inches to centimeter. I mean, it's like, okay, I'm just going to use this one conversion. But if you have a situation where you have multiple steps, that's where you may want to convert or add these little boxes. So general problem solving, we've already talked about this. Write your given, write what you're trying to find, devise a plan, make a solution map, and then sort, strategize, solve, and then always check. Okay, so let's do one that's a two-stepper, given what we know about units, our units thus far. So how many inches are in 1.337 meters? Now, is there a conversion factor directly between meters and inches? There is somewhere. I don't know it off the top of my head. But I do know the relationship between meters and centimeters, and I know the relationship between centimeters and inches because of that last slide we looked at. So I'm going to actually make this a two-stepper so that we can practice doing multi-step dimensional analysis. So we have information given to us in meters. We can pretty quickly go from meters to centimeters. And then from centimeters, we can go into inches. All right, how do we get from meters to centimeters? Well, right in here, I'm going to fill in that 1 meter is equivalent to 100 centimeters. Here, I know that 1 inch is equivalent to 2.54 centimeters. So this is sort of a two-stepper. let's write our given information. So given information here is that we have 1.337 meters. And we're trying to find inches. So we always start with our given piece of information. In this case, it's in meters. So we have 1.337 meters. Now, the first thing we're going to do is go from meters to centimeters. It's kind of like leapfrog. So don't worry about inches yet. Just focus on this first step of getting from meters into centimeters. And here's our conversion factor. Now, if you liked that King Henry died before drinking chocolate milk, where you just kind of moved the decimal around, that's fine as well. So my first conversion factor is this, and I don't know why it says 10, should be 100 centimeters, is to go from meters to centimeters. So 1 meter is going to be equivalent to 100 centimeters. What happens to my meters? They'll cancel. Now, some people will stop here and they'll solve and then they'll start back up. I like to chain all of my dimensional analysis together. So I'm going to go ahead and put in the next conversion factor. Meters have canceled. I'm in units of centimeters. Now I want to go from centimeters to inches. We don't have to think about meters in this hop here. We're just looking at the relationship here. So I'm going to chain in my next conversion factor. I want centimeters on the bottom and I want inches on the top. In this case, 2.54 centimeters is going to be equivalent to 1 inch. The centimeter unit will cancel and we'll be left with units just of inches. So remembering that your conversion factors, those fractions, those don't limit our significant figures. So we'll go with 4 sig figs. So I've got 1.337. I'm going to multiply it by 100. And then I'm going to divide it by that 2.54. And I get a long decimal, 52.63, so on and so on. I'm only going to take into account, I'm going to erase that, give myself some more space. The first 4 significant numbers. So the 5, the 2, the 6, there's a 3, but there's a 7 right after it. So I'm going to round that up to 4, 5.264, and my unit, which is inch. Sometimes you might see these written, I'm going to write the same thing here, 1.337 meters. You'll see it written like this, 100 centimeters, 1 meter, 1 inch, 2.54 centimeters. This is the same setup as this. Think of this bar here as your divisor bar, and then these bars as your multiplier bars. Okay, so you're multiplying and you're dividing. So you might see it sometimes written like that. In Pearson, I think they do that. So I'm going to give you a multi-stepper. And I want you to actually go through the process of making your little boxes. What are your steps that you're going to take and what your conversion factors are, and then put it in your dimensional analysis. And I'll give you about 4 minutes for it. So how many seconds are in 18.02 weeks? And if you know off the top of your head how many seconds are in a week, I guess you can do it in 1 step, but I don't have that sort of information rattling around. So you might want to break it down weeks, days, so on and so on. So I'll give you 4 minutes on that. Give you all another 40 seconds or so to finish up at least the setup. Okay, so I'm going to make a flow chart. We want to go, or well, our given information is that we have 18.02 weeks. We want to find seconds. I don't know a one-step relationship between those two, so I'm going to go weeks into days, and then day into hour, and then hour into minute, and then minute down into second. How many weeks, right? 1 week has 7 days. 1 day has 24 hours, 1 hour, 60 minutes, 1 minute, 60 seconds. So I'll start with my given 18.02 weeks. I'm going to take my first hop and get it into days. So we want to relate week to day. I want to get out of week into day. So week I want to cancel, so 1 week, and it gives us 7 days. Next step, day into hour. Okay, well, day will go on the bottom, so we can cancel it. Hour will go on the top, and then just give the magnitude 1 day for every 24 hours. Hour into minute. So for every 1 hour, we get 60 minutes. There goes my hour. And then from 1 minute, we yield 60 seconds. And we can stop there because that's the unit that we want. So we plug that into our calculator. In this case, it's pretty convenient because all we have to do is just multiply them all. 18.02 times 7 times 24 times 60 times 60. So this is the number that my calculator gives me. 10,898. Oh no, I'm sorry, 10,898,496. I've got to clean that up a little. Well, first, let me give it a unit. So this is seconds. Then I need to talk about significant figures. So this 1, 2, 3, 4 sig figs. Remember all these conversion factors, infinite sig figs. So the 1, the 0, the 8, and the 9 stay. I do want to keep the 9. The 8 is going to tell the 9 to go up, which then makes the 8 go up. So it's going to be 10, 9, 0, 0, 0, 0, 0 seconds. But in this case, this is significant, the 9 is significant, and that 0 is also significant, right? We said it was significant here, the 8 just made it round up. So if I want to represent it where just this 0 is significant and all these are just placeholders, I'll write it in scientific notation, 1.09, and I'm going to include just the significant 0, times 10 to the, let's see how many places we have, 1, 2, 3, 4, 5, 6, 7. And we're writing a big number, so we'll keep that positive. So 1.090 times 10 to the 7th seconds. And you just did a multi-stepper. Probably won't have any that are longer than that as far as multi-step, but you may have something that's, 2 steps, 3 steps. Any questions on that and on this whole dimensional analysis thing, how you got to get the units to cancel to make it work? No, everyone's doing okay. Looks like faces so far are like, yeah, I think I got it. Okay. back to the slides here. There's something I wanted to talk about. Here. Okay. So sometimes you may have to convert something that has like a 2 unit, or like this one here, 48.0 miles per gallon. Okay. Another way of writing 48 miles per gallon is to write 48 miles over, and we're kind of assuming that there's a fraction bar here, over 1 gallon. So the number, it always goes on the top value, a 1 always goes on the bottom. So if I say the car is going 60 miles per hour, that's like saying 60 miles over 1 hour. 1 always gets paired with the bottom thing. So if you want to convert this, let's say miles to the gallon is not useful because we're in Europe. So we want it to be in kilometers per liter. So I need to change my numerator to kilometers, which is what we are used to doing. Mile here, we're going to put the mile on the bottom and we'll put the kilometer on the top, so the miles cancel. The thing that's going to be different here is if we're changing the denominator, okay, if we're changing this thing, because it's on the bottom, I need to put my unit in such a way that the gallon will be on the top over here, because then it cancels with what's above, leaving the liter below, which is what we want. All right, so keep those sort of isolated. So let's look at this thing here, 60 miles per hour. I want you to change this, okay, or convert 60 miles an hour to kilometers per second, which is kind of a weird number, but just for the sake of practice, let me write it over here. You're given 60.0 miles per hour, and I want you to find kilometers per second. And then just so that you have it here, 1 mile is equivalent to 1.609 kilometer. Okay, because I don't know if you have that right off the top of your head. Hour to second, I'm going to expect you to be able to work that one. So I'll give you 3 minutes for that. Okay, so we've got 60 miles an hour. I'm going to write this a little bit different, 60.0 mile, and I'm going to put it over 1 hour or per hour. So you can start with either the numerator or the denominator. I'll start with the numerator and use this relationship here. So every 1 mile is equivalent to 1.609 kilometers. And what we'll see is miles go away and kilometers remain. Now I want to get rid of hour and convert it to second. So I'm going to do that in 2 steps. Hour is on the bottom, so I need to put hour on the top to get rid of it. So for every 1 hour, I get 60 minutes. And then I'm going to go even farther and go so hour cancels, and I want it per second. So for every 1 minute, I get 60 seconds. So you see how if you want to change the denominator, you kind of have to do it slightly opposite. You've got to go above to cancel. Now the units that are left, well, I've got a kilometer here and I've got a second here. Kilometers above, seconds below, that gives me kilometers per second. That's great. So we just need to plug it into our calculator. It shouldn't be a very big number because, you know, we're going in a car, so we're not going to go that far. So we take our 60, we multiply it by that 1.609, and then we have to divide it by 60 and then divide by 60. So 3 sig figs here. So I'll use 3 significant figures, 0.0268 kilometers per second. This 0 and this 0 are not significant. They're just placeholders to let you know how small the number is. Remember, precision or significance increases as you tack things on to the right. Any questions on this where you have 2 units, one over the other?
I have a question.
Yeah, what's up?
So I'm just confused. Like, I understand most everything except for in this particular equation, like how it all cancels out, like each thing that's being canceled out. Like I understand that the miles, because that one's above and that one's under, but then
This one and this one?
Yeah. Like how
do you see how in the very beginning it's miles per hour? Okay. So that word per hour, it means below a fraction bar. Okay, so it's 60 miles over 1 hour. So if we think of this as a fraction, or this right here is our divider. So this is sitting underneath your fraction bar.
Right.
So how things cancel when there's a fraction bar is under, over. So if this is under, I need to put it over here. This is on top of the fraction bar in order for it to cancel.
Okay. I was just confused because in the other equations we did it like the top one.
Top and bottom. Right. And so so normally when it's just a single unit, that's the system you'll follow, right? Top and bottom. But here it's already on the bottom, so you need to put it on the top.
All right.
You're not going to do a whole lot of these. You're not going to see this very often. Normally you're going to see it where it's just one unit and you just put it underneath to cancel it.
Okay.
Okay. Any other questions with that one? Or with dimensional analysis? Is dimensional analysis sort of making sense? Like, get how to cancel the units. Okay, cool. So there's one other thing that I want to go over in this chapter. Oh, here's this. We don't spend a whole lot of time with this, but there is a way to derive volume units. So if you know that 2.54 centimeters is equal to 1 inch, that's a unit of length. If I, for instance, wanted to convert this or turn it into a volume like centimeters cubed per inch cubed, I would cube both sides. All right, the cube gets distributed to everything. So it gets distributed to the unit, but it also has to get distributed to the number. All right, the unit and the number. So you can take something that's a length and turn it into a volume by cubing it. You could also take a length and turn it into an area by squaring it. So you cube both components. So 2.54 centimeters is equal to 1 inch, or 16.387 centimeters cubed is equal to 1 inch cubed. If you're dealing with a cube value, right, your information is given as a cube, you need to have the cubic relationship, not the basic length centimeter relationship. And this isn't something we spend a whole lot of time working on, but you may see something pop up on your homework. I don't put anything on the test that's cube related for you guys. So we're going to kind of just brush over that. The next thing though, we do want to talk about physical property known as density. So why do some people pay more than $3,000 for a bicycle made out of titanium? And the answer that I get a lot of times in person is because it's light. Well, or, it weighs less. Well, I can have a bike that's about as big as my fingers. That's really, really light, right? But it's also very, very tiny. So it's not a very useful bike. So the thing that you want to actually get at is that the bike has a lower density, or it's got the same volume, right? It's a person-sized bicycle. It's not a bicycle made for an ant. It's a bicycle made for a person, but it weighs less for that given volume. And that means that it has a lower density. So when we look at something out of titanium, titanium has about 4.50 grams per centimeter cubed. Remember, when looking at a double unit like this, the number goes with the gram. The thing underneath the fraction bar gets a inferred 1. So it's 4.5 grams for every 1 centimeter cubed. This is much less dense than, say, iron, which is 7.86 grams per every 1 centimeter cubed. Right, so less mass in the same volume. So here is an equation for density. Density is one of those things that you could solve either using dimensional analysis or the equation. I usually just use the equation because it's 3 variables. It's sort of easy to plug and chug. So density equals mass over volume, or D equals M over V. If your mass goes up, your density goes up. If your volume goes up, your density goes down if the other stays consistent. What are some units for density so that we don't get freaked out when we see these things? Grams per centimeter cubed, kilograms per liter, pounds per inch cubed. Okay. All of them are some sort of mass value. I know pounds aren't mass value, but sometimes we use it as a mass. It's a mass divided by some sort of unit of volume. So you could see it in a bunch of different ways. Are there more densities outside of this? Yes, there are. This one we tend to see a lot though, this gram per centimeter cubed. One thing I want to note, a centimeter cubed is equal to 1 milliliter. It's also equal to a cc. Okay, so if you hear cc, it's talking about a centimeter cubed. There's a direct relationship. 1 centimeter cubed is equal to 1 milliliter. So let's see a problem here. We calculate the density of a substance by dividing the mass of a given amount of its volume. So if I have a sample of liquid and it has a volume of 22.5 milliliters and a mass of 27.2 grams, and we want to find its density. Hold on 1 second. Melissa, that's fine. Just hang out after class and we'll chat. So density equals mass over volume. So we would take our mass value, put it on top over our volume value, and we divide it out. Now with density, make sure you've got a double unit. Okay, don't 1.21 grams and you're like, I'm not going to include milliliters. That's talking about a mass. If we want it to be a density, it's got to be mass per a given volume. Could you be given density and mass and solve for volume? Totally. Could you be given volume and density and solve for mass? Yes. So there's 3 variables. You'll be given 2 and you have to solve for the third. This is going to be my 2 cents on isolating variables because I know people haven't done math, some of you haven't done math for a while, and isolating variables Not something you've done, but in a while, but if we've got density equals mass over volume. If I want to isolate for mass, that means I want to get mass by itself because I'm trying to solve for it. What I need to do, I'm going to circle it here. I want to get it by itself. So to get it by itself, I have to take volume and move it to the other side. How do I move it to the other side? Well, whatever it's doing on this side, I do the opposite. So on this side, the volume is acting as a divisor. It's below the fraction bar. So I'm going to multiply this side by volume. Volume will cancel. Whatever I do on one side, I have to do on the other side. So mass now equals density times volume. If I was to want to solve for mass, I could get density times volume. If I want to solve for volume, that one tends to be a little bit trickier for people. Density equals mass over volume. So I want to get volume by itself. All right, well, mass here is acting as a multiplier, so I could divide this side by mass, but that means I need to divide this side by mass as well. Mass goes away, and I get density divided by mass equals, look at where volume is. Volume is below the fraction bar, so I actually have this as 1 over volume. I don't want it to be 1 over volume. I don't want the inverse of volume. I just want volume on its own, so I need to flip-flop these guys. So mass over density will equal my volume. A lot of times what happens is people will take this step from here to here and they'll say, oh, I've moved my mass over, so density, so volume equals density over mass. That is not the case. You won't get the right answer. So you've got to make sure you're isolating correctly. You can see it over here. We've got mass equals density over volume. If we want to get volume by itself, I would divide by density and divide by density. Density cancels and I get volume equals mass over density, not density over mass. It will mess your units up and it will mess your answer up. So that's my 2 cents on isolating variables. Oh, you know what? I'll do this too. I think this is helpful for some people. You can draw a little triangle. And we're going to cut it into 3 spots. Density, mass, volume. Think of this as a divider. Think of this vertical as a multiplier. Okay. If I want to solve for density, density will equal mass divided by volume. Okay, if I want to solve for mass, mass will equal density times volume. If I want to solve for volume, which is this guy over here, volume equals mass divided by density. That's just a visual way of doing what we did over here. If this freaks you out, you're not a huge math fan, you may like the triangle for isolating the variable. So let's do a couple density problems. I don't know if the slides actually have a problem that we can work. Yeah, let's do this one. Okay. For a liquid substance with a density of 1.32 grams per centimeter cubed, what volume would be measured to deliver a mass of 68.4 grams? So I want you to go ahead and solve for this. You're looking for density. You're given the other information. This is an equation problem or where you're going to plug and chug. We'll give you 3 minutes to work on that one. Okay, so I'm gonna write it over here. It's just easier. My pen works better in this program. So in this problem, we're given two pieces of information. We're given the density and we're also given the mass. And you just want to start getting comfortable with seeing certain units and associating them with certain things. So gram is a mass value, not a volume value. The problem says, hey, find volume. So we know our equation is density equals mass over volume. Using our little triangle or isolating, volume is going to be equal to mass divided by density. So I like to solve it this way. So I'm just going to plug it in, right? We've got our density and we've got our mass. One important thing to do is make sure the units are the same. Okay, so this is grams per centimeter cubed. If this value happened to have been in kilograms, you can't plug it into the equation. They've got to match up. So you'd want to convert from kilograms to grams. And I can give you guys a problem like that in a minute. So we just stick it in there. All right, here's my mass, 68.4 grams. I always add my units, divided by my density, which is this 1.32 gram per centimeter cubed. Look at that. Grams are going to cancel. And then centimeter cubed is below this fraction bar, below this fraction bar. Anytime you're below two fraction bars or two dividers means that it moves back up to the top. So my unit will be centimeter cubed for this. So I just take that 68.4 and we divide it by the 1.32. We get a value of 51.818181. Well, we get to use 3 sig figs. So we're going to go with 51.8 centimeters cubed. The textbook talks about using density as a conversion factor. Anytime you have a value that has 2 units like this, it can be written as an equality, right? So in this density case, it's saying we have, sorry, let me get my pen back. 1.32 grams per centimeter cubed. That's like saying 1.32 grams for every 1 centimeter cubed. It's a conversion factor. So the text talks about solving this using dimensional analysis. You would start with your given information, which is 68.4 grams. And you multiply it by this thing as a conversion factor. So I'm actually going to flip it because I want the gram to go on the bottom. So 1.32 grams for every 1 centimeter cubed. What happens to grams? They cancel and you're left with centimeter cubed. You're taking the 68.4 and dividing it by the 1.32. It's the same thing you've done here. I don't find this as intuitive, and I find that for students in general, it's not quite as intuitive. So I sort of stay away from this and just go with plug and chug in the equation. But if you see that somewhere in the text where they're saying, hey, make it into a conversion factor, that is what's happening, but you're doing the same thing. Okay. So let's do another one. A liquid takes up 1.82 liters and has a density of 3.47 grams per centimeter cubed. What mass of liquid do you have? Hint, hint, wink, wink, be checking units, okay? I'll give you 3-4 minutes for that, and then we'll cover that. All right, so still a density problem. You know, anytime you see things where it's talking about density and volume, you might just want to write out the equation density equals mass over volume to remind you what you're doing. Given, we've got two things here. We've got 1.82 liters, which is its volume. We also know its density. So the density here is equal to 3.47 grams per centimeter cubed. Now, we're trying to find the mass, right? So what is mass? Mass is going to be equal to density times the volume. These are not the same units though, okay? This is in centimeters cubed, this is in liters. So I need to convert. I'm going to convert this. It's much easier to convert something that only has one unit than something that has two units. So could you convert the density into grams per liter if you wanted to, but I'm just going to convert liter into milliliter, or liter into milliliter. And then milliliter is the same thing as a centimeter cubed, right? We said a centimeter cubed and a milliliter are the same thing. So if I want to get from liter to milliliter, King Henry died before drinking chocolate milk. We're at liter, which is, this is B, the base. I want to get to milliliter. So hop the decimal over 1, 2, 3 spots, 1, 2, 3, or 1,820 milliliters. Now a milliliter is the same thing as a centimeter cubed. We said cc is the same thing. So I can just say it's 1,820 centimeters cubed. I like this matching this. It's not even that I just like it, you have to, or you won't get the right answer. So now we're going for mass equals density times volume. So mass should equal my density, which is 3.47 grams per centimeter cubed, times my volume in the correct units, centimeter cubed. And look at what happens. Because the units are the same, they're going to cancel out, and I'll be left with just units of grams, which is a great unit for mass. So 3.47 times 1,820, we get 6,315.4 centimeters cubed. As far as significant figures are concerned, I have 3 sig figs. So I'm going to keep this over. I'm going to keep the 6. I'm going to keep the 3, the 1. The 5 tells the 1 to go up to a 2. Fill it in with the 0 centimeters cubed. Any questions on that? If you were to have just plugged your numbers in without converting the 1.82 times the 3.47, you would not have ended up with the right number of centimeters cubed. All right. And you would have gotten to this place here. And that's why I always tell students, write all your units in, write everything in, because if instead of writing this, you had written, you hadn't thought, oh, to convert, and you just wrote this in 1.82 liters, well, you'd get to this place and go, liter isn't canceling with centimeter cubed. Something's not right here. So that's why I always like to have the units, because then I realize if I've set something up incorrectly. Any questions on that? On density? Okay, so that gets us through chapter 2. You do have, while we're here together as a class, let's look at the syllabus so that we're just all on the same page. We won't always be going over the syllabus every week, but just for the first week or two. Check it out. Okay, so the syllabus did say that we were potentially going to start chapter 3 this week. We didn't, no worries. Next week will be more than enough time to get through all of chapter 3. So some due dates. You've got experiment 1 measurements due on Sunday. So make sure you get that done. You've also got the quiz that's associated with that. Where do you find the measurements lab? You have the physical manual that you bought from the bookstore. You will fill that out and then you will submit it to me as a PDF on the Moodle page right here. So this is where you will submit that lab. The quiz that goes along with that lab is just underneath where you submit the lab. So you'll click on that. That will actually guide you through questions that you'll answer through Moodle. So make sure you're getting those 2 things done. And then you also have a Mastering Chemistry assignment, chapter 2, that will be due as well. It will cover dimensional analysis, density, conversion factors, prefixes, all that fun stuff, okay? We'll start chapter 3 next week. We will meet on Monday. Okay, so this week was a little bit short. Didn't get to see you guys for a whole lot of time, but we got through what we needed to get through. So we are good for the week. If you have questions, stay around and I can help you all individually. Otherwise, enjoy your weekend again and enjoy the rest of the day. Beautiful day. Okay, so I will talk to you all next week. Bye-bye. And Melissa, I know you had a question, so feel free to stay around. Anybody else does?
I have a question about turning in the labs.
Okay, I'm going to put you in the waiting room for a second. I'm going to help Melissa out first, and then I'll bring you back in, okay?
Thanks.
What's up, Melissa?
Hey, sorry. It's
No
been a
worries.
rough. I've started this lab assignment, but then we just found out yesterday my grandmother has cancer, so it's been my brain is like completely
Oh, I'm so
lost.
sorry. I'm so sorry.
On the smallest markings. Exactly. I knew we went over this in class, but I'm not exactly sure. Like I told you, my brain is completely. I have my aunt and my grandpa both like calling me for all these questions.
Mhm.
So I'm just not understanding like the smallest marking.
On a ruler?
Yeah, that's centimeters, correct?
The smallest marking, it's kind of hard when you don't actually have a meter stick in front of you. So you've got you've got a meter stick. The meter stick is traditionally divided into tens, right? So that would be the decimeter. Then the smaller markings are going to be, there'll be 100 of those. Those would be the centimeter. And there's actually a smaller one. So each centimeter is broken up into 10 of themselves, which would be the millimeter. So when you have a real meter stick in front of you, you will actually have the smallest tick will be the millimeter. There'll be 1,000 of those bad boys on there. At least the meter sticks that we had in the lab.
All right. Thank you.
Yeah.
Okay.
Any other questions?
Thank you. That's all.
Okay. I'm sorry you're going through a rough time right now. Good luck.
Thank you.
Yeah.
Thanks.
Take care.
Bye.
Okay. Liza?
Yeah.
Hey, what's up?
I had a question about turning in the labs.
What's up?
So I think the video said to like turn it in through a PDF thing. And so I took pictures of the lab to turn it in. And I could turn it in separately, but it'd have to be like each page separately.
That's how I want you to submit it, is each page separately.
But when I tried to turn it in, it only let me do one PDF, which was only one page.
Let me see. So there is a way to merge your PDFs, the multiple pages into one PDF. Let's see. So experiment 1. I'm just pulling up the settings on it now, making sure that you can submit more than one page. Yeah, this says the maximum number of upload files is 20. So you should be able to submit more than one PDF. So if each page is being saved as an individual, you just have to submit each one.
Okay,
Okay?
thank you.
Any other questions?
No, that's it.
Okay, have a good day. Have a good weekend.
You too.
Bye.
Bye.